Hey y'all, welcome back to part two. So looking at static friction. So static friction and kinetic friction obviously are both friction forces. Kinetic friction deals when an object is sliding or already in motion against another object or surface. Static friction is of course when it is not moving. So this is when we talk about things that need to be overcome, frictional force and all that. So static friction keeps objects from moving when a force is first applied. Unlike kinetic friction, static friction is not a constant force. This is one of the most interesting things about this kinds of friction, but it exerts only as much force as is needed. So here's a quick example. You have an object in front of you, whether it's a table or your laptop or whatever, and if you push it with just a tiny amount of force, it won't move. Newton's third law says there's an equal and opposite reaction to that. I can continue to increase the friction force, or the force of push that I'm acting on it. I push harder and harder and harder until eventually it does move. So static friction can reach a maximum value here, and that's typically what we calculate when we're looking at problems. The formula for this is very similar to the other one. Oops, wrong pen, sorry. The friction force for static friction is mu s, again, times the normal force. The coefficient of static friction, it depends on the types of surfaces. And once again, the normal force is the contact force between the object and the surface. So we have the same idea in terms of calculating. The friction force increases as the applied force. So there's a thing that we can say the friction force is going to be less than or equal to mu times the normal force. In other words, that's how we express that maximum value. If I get bigger than that, the object moves, and then it takes over to kinetic friction. So what we do is we end up solving this equation to determine what the maximum friction force is, and then apply whatever rule we're looking at applying here. Here is just a quick chart showing the difference of static and kinetic friction. This is again saying it's harder to get something to move than it is to keep moving. So a big heavy object sitting on the floor, once I get it moving, the kinetic friction takes over. So notice all of these kinetic friction values are greater or less than, their static friction counterparts. Notice over here, this is kind of an interesting thing. We have rubber on other solids can get really big. Typically it's always less than 1, but you can have several instances where that becomes really hard to move. So anyway, there's an idea of how we handle that. So let's take a look at some static friction examples. We have a block sitting on the table. So once again, let's use our free body diagram here of my mass. And I know I have Fg pointing down, and I have my normal force pointing this way. And I have the coefficient of friction between the surfaces is 0.7, so mu is 0.7. That is static. I have a mass of 5 kilograms. And it says, what is the largest force that can be applied horizontally before it moves? So the force of friction is calculated by mu sub s times the normal force. I know that my normal force and Fg are the same. So mu mg. So let's crunch this number. I have 0.7 for my coefficient. I have 5 for my mass, 9.8. So I get a value of 34.3 newtons of force. So that is the largest force that can be applied. So what that means is if I push with 1 newton of force, it won't move. I can push with 34.2 newtons of force, and it won't move. But the instant I go over, so if I push with 35 newtons of force, I then have a net force that accelerates the mass. So that's an interesting idea to make sure we understand there. But the way this question is written, this is the maximum force that can be applied before the object moves. So let's take a look at the second example here. We have a block sitting on a table. I have the coefficient of friction, and then I have a 10 Newton horizontal force. So let's see, I have the mass of 6 kilograms. I have the coefficient of static friction of 0.6, and I have a force of 10 newtons. So for good measure, let's sketch the free body diagram. The pushing force that way and the friction force this way. So first off, I got to figure out what the max force of friction is before I can figure out if it's moving or not. So there's my friction formula. So the max value is going to be, let's see, 0.6. I'm cheating a little bit. I know that's mg. So the friction value should be about 35.3 newtons of force. That is the max value I can push on. Notice the way this question is written, it said I'm only pushing with 10 newtons of force. So since, I'm going to write it kind of long here, since 10 is less than 35.3, the object will not move. However, the question asks, what will the force of friction be on it? Well, because it's not moving, if I push with 10 newtons of force over here, the friction force applied will also be 10 newtons of force. Remember, the static friction can be whatever it wants to be up until that critical value where it starts to move. So in this case, because the 10 newtons of force was not sufficient to overcome static friction, the object will not move, and the force of friction applied will be 10 newtons. That's cool. So on this question, if you kind of see in your notes, it has a lot of what ifs over here. And what's gonna happen is that the first two behave exactly the same way, and then the third one, something kind of interesting happens. So let's take a look at what's happening here. We have a stationary object of 250 kilograms, and I have the weight of the object and the normal force of the object. I have two coefficients of friction. I have the static as 0.3 and the kinetic as 0.15. So the first thing I'm going to do is I'm going to calculate how much force is required to move the thing first by using the static friction. So 0.3, the mass is 250. So when I crunch that number, let's see, 0.3 times 250 times 9.8. I get a maximum value of 735 newtons in order to push it. Once it's moving, however, the force of friction is this, 0.15, the same mass, the same gravity. I get a force of friction of 367.5 newtons once it's moving. So, over here, this is what I have to overcome in order to move it. This is what's happening once it's moving. So with that in mind, let's take a look at our question here. We have already kind of drawn the free body diagram for this one. Let's assume we did that. So on this question, we have a horizontal force of 300 newtons applied to the object. Well, in this question, the force of friction is going to be 300 newtons of force. I wasn't able to overcome my 735 Newton force over there. So that's something to keep in mind there. Acceleration of the object, well, I didn't get it to move, so it's 0 meters per second squared, it doesn't move. Part B, notice, same kind of question. The force of friction I need to overcome is 735 newtons. I'm only pushing with 500, so the force of friction is 500 newtons. It doesn't move. Acceleration is still 0. So those first two wasn't a strong enough push to overcome it. Part C is a bit more interesting. The free body diagram of this looks like so. The gravity, the normal force, the 750 Newton push this way. And because this value was greater than my static friction force, I have to use this kinetic friction here to make my problem work. So in this case, the force of friction being used is that 367 number. That is the kinetic friction that's acting on the object. And then to determine the acceleration of the object, that is an application of Newton's second law. The net force is from the pushing force minus the friction force equals ma. In this case, I have 750 minus 367. The mass of the object was, I can't remember, 250. So when I crunch that number, I should get an acceleration value of about 1.53 meters per second squared directed to the right. So on these questions, they're kind of interesting. They employ both of the static and kinetic ideas that if I don't push with enough force, it won't move. But however, like in part C, when I do push with enough force, the object does end up moving. All right, so there's our part 2 for our static notes. Thanks for watching. Let me know if you have any questions. Thanks, bye.